Okay, good morning all of you. So welcome back to laser technology session. So in the last class we have discussed about the Gaussian beam. So we will continue how the Gaussian beam and Gaussian beam profiles and their parameters. So as we know from many of the laser systems in the practical lasers, the fundamental mode is a Gaussian mode. So that is TM00 mode. So you take a laser beam and you diverge it using a diverging lens. So then you can see on the photographic plate, you see the mode. Because these are high intense beams, unless you diverge, it is very difficult to see the mode. So if you plot any direction, so your distribution follows the in Gaussian shape. Okay, so that means the transverse electric field magnitude is your Gaussian function. So now you can represent this equation in this expression form. So your E of Rz, your R is a radial distance and Z is along the propagation direction. Your electric field will be distributed like this. Your E naught is your amplitude of the electric field, and W naught by W of Z, e power minus R square by omega Z square, and e power minus I kz plus k R square by 2 Rz minus phi g. We will go in detail one by one. So your R is the radial distance from the center axis of the beam. So now if you have a beam in the 2D plane, the center axis from the center, whatever the distance you go in either directions in 3D, so that gives you a radial distance. That will be the one plane, that is xy plane. So that's why your R square is equals to x square plus y square. Okay, that means if you have a spherical shape, you take the cross sectional, each cross section that represents your plane, that will be falls in the xy plane. So because your electric field, the polarization component is always in xy direction, because that is your transverse mode of the electromagnetic waves, the beam is propagating along z direction. Okay, so that's why as your radial distance changes, so this will e power minus R square by omega Z square plays a crucial role. And here e power, this whole component is represent the phase of the wave. So this whole gives you your amplitude and this whole gives you your phase. So now your amplitude is a complex amplitude. So not only simple a constant E naught, this amplitude is a complex in along your spatial directions. So that's why your Gaussian beam amplitude always a complex profile. And this factor is whole which determines the phase of your electromagnetic wave. That is your radial distance, and k is your wave number, so 2 pi n by lambda. So for the free space wavelength lambda, so where n is refractive index of the medium in which the beam propagates. So sometimes we also call as a k is your wave vector. Okay, in both cases both are the same. In the units of wave numbers, it's 1 over lambda is your wave number. The remaining is a constant depending upon your material medium when it propagates. So you can call the k as a propagation vector, or you can call as a wave number. And E naught your electric field amplitude at the origin at time t0. Okay, so that is your E naught, but this whole factor is your complex amplitude of your Gaussian beam. Okay, so now W of Z. So the W of Z is the radius at which the field amplitude falls to 1 over E of their axial values. So in principle, you can call W of Z is kind of a diameter. We will discuss in the later slides. So what exactly W of Z is. Okay, so then also as Z changes, your beam width changes. Okay, so that means you always associated with certain divergence to the propagating laser beam or a Gaussian beam. Okay, so you always have certain divergence, so that W of Z will changes as you propagate along the G direction. So now the W of Z is defined as W naught into 1 plus Z by Z naught whole square and whole power 1 by 2. And depending upon W of Z, your intensity, so your intensity is nothing but, we know if we know the electric field, your intensity will be electric field and its complex conjugate, right? So now you take these vectors, your E naught square gives you I naught, and this whole factor will be squared W naught by WZ whole square, and now this e power minus r square WZ square, now this is two terms, so because in the e term also there and e star will be there, because now it two times of this term, so this is e minus 2r square W of Z square, and this factor will be cancelled out because whatever the phase accumulation in this E, and E star becomes a plus. Okay, so minus I becomes plus I in the E star, so that will cancel out. So now your intensity will be remain like this. Okay, so that is your intensity as I of RZ. R is your radial distance and Z is propagating direction. So your intensity is varying along Z as well as your radial distances using this formula. Okay, so now if your I of RZ can be written as, we know what is W of Z, so you substitute your W of Z is like this, so then you will get this expression. So your W naught get cancelled, your I of RZ equals to I naught 1 by Z plus Z naught whole square and e power minus r square W of Z square. Okay, so now if you take a Gaussian beam, okay, you try to focus it. So when you try to focus it, so this is the way the Gaussian beam will be focused. So now for example, this is your Gaussian beam in a cross sectional view I am taking. So you are focusing using a lens. Now this is the beam focus will happens like this. So this is around G direction. You are propagating the beam along the Gaussian beam along the G direction. So now this is your WZ. Okay, this is your WZ, and this W naught is from the center of the beam to one of the edge, and also remember that is at the position 0. That means it's a focal point. At a focal point, the distance from the center of the beam to edge is defined as W naught, and the distance from the center, that means our focal point to Z naught. So this is our Z naught and this is our minus Z naught. So this is positive direction, this is our negative direction, negative Z direction. Okay, so this is our focal point is our center, it's 0. Okay, now from center to certain region, that is around root 2 by W naught. So where your W naught increased by root 2 times, so that is your Z naught. So this is positive Z naught and this is minus negative Z naught. So Z naught is called a Rayleigh range. So now you see your intensity will be, as Z increases, it changes. As your Z changes, because the propagating direction is changing, your intensity also will change. So your W naught is our called beam width radius. So now for example, at this center you can see, so this is full width, that you call as actually it's beam width. A 2 W naught is called beam width and W naught is called beam width radius, or you can call west radius, that is W naught. Okay, W naught you can measure by lambda Z naught by pi whole for 1 by 2 for the Gaussian beams. So your W naught will be as much as short it is possible when you tightly focus it. Okay, so now your Z naught is called Rayleigh range. Okay, so the Rayleigh range means from the distance from the focal spot to where the beam size or your W naught, beam width radius, will increase by root 2 times. So that is called Rayleigh range, and 2 Z naught is called depth of the focus. So now from either sides you have a Rayleigh range. From the center you have this direction, your beam size increased by root 2 times, and this direction also your beam size increased by root 2 times. From the center you can see it's either directions it has a symmetry. If you see one direction, that is same replica, you can mirror image you can see on the other side. So either sides your beam diameter increases from the focal spot. So now your root 2 omega, where it is root 2 times of your beam width radius, that length you call a Rayleigh length or Rayleigh range, and 2 times of your Rayleigh range is called depth of the focus, or also called a confocal parameters. Okay, so now the radius of the curvature of the wavefronts, I think that we will discuss later. So your beam divergence, now if you see your beam is diverging from your focal spot in either directions, right? Because this direction you are focusing, this direction it is diverging. So now you can calculate your divergence angle theta naught, that is our lambda by pi omega naught. So if you remember in the previous laser characteristic sessions we discussed, it's a lambda by d, it's closely to lambda by d. So that you see here, now I am multiplying with the 2 factor, 2 lambda by pi 2 omega naught. Your 2 omega naught is almost your diameter, so that is at the focal spot, this is your beam width, right? So now you get 2 by pi lambda by d almost, right? So this is your divergence of the beam divergence of your Gaussian beam. As beam propagating from its focal spot, so now you have a Gaussian beam, and as you see the beam is actually the size wise it is decreasing, and at the focal spot it reaches the minimal spot size or its minimum beam width, then again it is increasing. Due to there will be high intensity variations appears. Due to high intensity variations you accumulate the phase, also you call phase retardation. So now what happens, this phase retardation appears, that phase is called Gouy phase. Okay, as you propagating along z direction, at the focal plane what happens, your phase velocity dominates. As your phase velocity dominates, it appears a phase retardation. That phase retardation is defined as a Gouy phase. So that is pi of g is equals to tan inverse z by z naught. Z is your propagating beam direction. At different positions you can calculate the Gouy phase shift like this. So now along z direction, this is the Gouy phase shift. Okay, this is pi by 2 and minus pi by 2, the shift in I plot along the y axis. Now as you see, as you propagating, okay, as you propagating along the focal line, focal region, I am mainly focusing here on the focal region. Okay, in the focal region what you see, your phase is changing as you propagating, and again you have retardation. Now you have a phase shift. Now if you see, if you go to the far field means very far away from the focal point. So if you go this direction very far, okay, that is, for example, it's a 5/4 compared to your plane wave. So because when the wave is coming from far large distances, always it has a phase of a plane phases, so that it gives you a plane phases. So those plane waves are coming in, right, at the far distances. Compared to your plane wave phase, this phase shift appears when you propagating this far field radiation. Now you see, for example, this side is a minus pi/2 phase shift, right? And now you propagate this region, it will, over the large distances you travel, you accumulate by pi/2 again here. So that minus pi/2 to pi/2, that means you have the phase shift of 180, that is your pi phase shift appears from far field and this direction from the focal to other direction of the focal point. You get, say, a pi phase shift. So this can be observed in many of the experiments. Some of the experiments it doesn't show, but in principle, okay, this Gauy phase shift can appear in the Gaussian waves due to their phase velocity domination in the focal plane. Okay, I hope you know about the phase velocity and group velocity. So your phase velocity is nothing but your omega by k, and group velocity nothing but d omega by dk. That means it's like a wave. When you talk about in quantum mechanics, you have wave packet. So wave packet is propagating, then that velocity is your group velocity. Okay, only one wave, you consider one wave in the group velocity in the wave packet. So each wave having different velocities. Okay, so that we call as a phase velocity. Okay, so now in this case, at the focal region, your phase velocities will dominate. So that is the reason this phase shift will appear. We see about the radius of the curvature. So now you know that your waves have wavefronts. As your wave is propagating, so we can represent with the wavefronts. So your wavefronts will be, for the Gaussian beams, defined as R of z equals to z into 1 plus z naught by z whole square. Okay, so that means if you assume now you want to measure a plane wave, or you want to measure a wavefront at z equals to 0, that means at exactly around your focal point. At this point, I want to measure the radius of the curvature. So now at this point your z equals to 0. So at z equals to 0, what happens in this equation? You substitute z equals to 0. So your z naught gets cancelled. So that means you get 1 plus 1. So that is nothing but z equals to z naught. So you will get your radius of curvature is equals to 2 z naught, and we know that z naught is a constant, right? So your 2 z naught is a constant, you will get a constant phase. So which one have constant phase? Your plane waves have constant phase. So now at this center, at this focal point, z equals to 0, your wavefront is plane wave. Okay, and very close to z equals 0 also you will get, in principle, up to till this region your wavefront curvature will be very small, almost close to plane waves in the focal plane, or you can call it the depth of the focus. Almost your phase is constant within the beam. As you go away from the focal plane, so your radius of curvature will increases either sides. Okay, so as you see in the focal region, your plane it almost close as a plane wave. At the focal point, we are very sure that you have a plane wave. It's very nearby, you always have a close by plane waves, and as you away from your depth of the focus, you will see the curvatures. He has wavefronts of spherical wavefronts. So that is why we call this Gaussian beam's amplitude is complex. As you propagating along z direction, it will changes. And not only, see, your phase also will be also depending upon your focal region. So your some of the, like for example, as you see in the equation, in the previous equations, so your phase is depending upon many factors as it propagating. Now you see there are, so one is a Gouy phase shift, it gives you a retardation of the phase, and this along propagation direction kz as well as your radial directions will give you the phase shifts. Okay, so this is actually in a Gaussian beam is a complex form. So that is the reason I am explaining each individual terms, how your intensity is changing, how your radius of curvatures are changing in the Gaussian beam profile. Okay, and what are the main parameters we discuss, like for example Z0 is your Rayleigh range, so or you call it the depth of the focus, because at the depth of the focus your intensity is almost constant and also high. So that we discuss in the next session, next class, or if you have time maybe we can discuss now. So this way your radius of curvature will change as it propagating along either directions from the focus. Now if you see the radial intensity distribution now, so this is for example my at Z0, and this is at a certain Z position or Z1, and this is certain position Z2. So now if you see this is your x and y directions, so this is your radially, now this is your beam profile. So at the center you have a high intensity, at the center you have high intensity. So now this is, if you plot, this is intensity. Okay, so now if you see this is your radial position, this is the distribution, intense distribution. Now at this certain position, like you move certain distance from the focus, now your beam starts diverging because you tightly focused. So now what happens, your peak intensity decreases. Now you compare with this focal spot, your intensity is high, your peak intensity is so high, and you compare with after traveling certain distance, it has a spread, but overall what happened, your peak intensity decreased. Even if you go further, your peak intensities will decrease. Okay, that means that at the focal point you have very high intensity. At the focal region, that is very important, that you will get very high intensities at the focal region. Okay, when you want to image any, like for example in non-linear imaging, you want to see, you will see in the focal region. So because at the focal region we will get very high intensities. As you propagating along propagating direction on the either sides from the focal point, your beam sizes increases, and eventually the intensity of the beam decreases, the peak intensity of the beam decreases, and still they follow the Gaussian profile, but as you see, your peak intensity or varies from a focal point to away from the focal point. Okay, so that now if you understand clearly, it is giving a flexibility to play with the intensity. So now for example you want to excite your medium with the intensity dependent variation. Now what you can simply do, you place your sample or your material and you just, this is your sample, so you just move around the focus, then your sample experiences intensity dependent variations. So this flexibility we will get. So there are many applications using the Gaussian beams. So this is one of the applications. So you will get intensity. For example, you want fixed intensity, you can always fix the position of the sample, or if you want intensity variation, you can move the sample along your focal plane. So this is our the intensity distribution, and your intensity along only axial direction. Axial direction means along propagating direction, only I of z. Then you can make your R component is 0. So your radial distribution is intensity is, you assume R equals to 0. Then your I naught into your e power whole component will becomes 0. That means you will get I of 1 by z plus z naught whole square. Okay, so now at the focal spot, so that means if z equals to z naught, if you place at z equals to z naught, that means at the Rayleigh range, what happens, you will get your intensity will be reduced to I naught by 2. So at the Rayleigh range, now you have your Gaussian beam focusing spot. This is your Rayleigh range. So at this point, like you have a highest intensity, now your intensity will be reduced by half at this point. So you will decrease the intensity, your peak intensity by half at your z naught. That means at the end of your Rayleigh range, your intensity decreases by half. So now you can calculate your laser beam power. So in general, in practical purpose, we always calculate the power. So from the power we will calculate the intensity. So now your power is a measuring parameter. So your power is nothing but you integrate from 0 to infinity in the radial distribution as well as your g direction, and with the 2 pi r dr. Okay, this is your surface area of your beam size. So then you integrate, we know that what is I of rz. So from this you solve this and you will get your power is in terms of I naught pi omega naught square by 2. So this is your power. So once we get the power, from this we can calculate the intensity. So this is a general expression we use to calculate the intensity once we know the power. So we have the power meters, practical power meters, to measure the power.